All right, we are ready to go, I guess. Let me turn on the projector. And just a couple of things. This is just sort of rubbing in a little bit. In my trig class that met just before this, actually on Tuesday, a student turned in a research paper, first one of the term. We hadn't even met as a class. They had been here, but they read, on YouTube like y'all did. And he already got the information and got it done and turned it in Tuesday. And then this morning in my 112 class, pre-calculus algebra, another student turned one in. So keep them coming. Yeah. That's hint. Let's keep them coming. All right. Any questions for anything we did last time? Okay. So for now, it's just you and me. So this is going to be probably somewhat. Last time we did on page 4, it's called Systems of Linear Equations, and we went through and solved 2 lines. We did solve the system of equations, just 2 equations, 3x minus y equal 1, and 2x minus y equals 0. Okay? This time we're going to do a slightly different one, and this is, let me get my pen set up. Okay? 3x minus y is equal to 1, same as before. But the second, well, we do have somebody else here today. Peyton's really happy to see you, so he doesn't have to answer all the questions. Except Mrs. Terrell. No, I'm sorry. Okay. All right. The second equation now is 3x minus y is equal to 0. Okay? Now, it says repeat the analysis for this pair of lines. Okay? And then there's another pair. Okay? Can you tell me anything just looking at those 2 equations, that system of equations? Anything that reaches out and grabs you, strikes you, impresses you, you notice about that?
You can solve for x on the bottom pretty easily, it looks like.
Okay. Frankly, I would solve for y. It's even easier.
Solve for y is
yeah. Okay. Yeah, and that would be y is equal to 3x. Okay. Is that right? Okay, and then you could plug that back into the top one, couldn't you? And that would be 3x minus 3x is equal to 1. And how often is that true? Never! Okay. In fact, if you looked at that closely, you see 3x minus y equal 1 and 3x minus y is equal to 0. That can't happen either. The same expression on the left can't be 2 different things on the right. Okay? Yeah. So, what could you conclude about this system?
It is unsolvable.
Okay, absolutely no solutions. Now, the way they were suggesting doing it is graphing it, which I was resisting with every ounce that I had in my body. You get 2 parallel lines near the twain to meet. They both slope 3. They both, have y is equal to 3x. But one has a y-intercept of 0, meaning it goes to the origin. The other y-intercept of 1. So never the twain do meet. They don't ever cross, no solutions. Okay? Just one number different, and you got that. Then they had this one. 3x minus y, I can't write, is equal to 1. They like that one. And 6x minus 2y is equal to 2. Okay? Now, what would you do with that one?
3x minus y is 1. That's 6x minus 2y is 1?
Yeah, 6x minus 2y is 2.
I would try to solve for y in the bottom one by first dividing by 2 and then moving y over.
And what does that give you?
So that gives you 3x minus y to the 1, which is identical to the top one. So that's all solutions.
Yes, every solution to the top is a solution to the bottom and vice versa. Now, not everything is a solution to that. All the ones that work on one are going to work on the other. So if you graph those, they're on top of each other. They're the same line, okay? They're exactly the same line. So that one has an infinite number of solutions. That one has no solution. The one we did last time had one and only one solution. And those are the three possibilities when you have two equations, two unknowns.
And they're linear.
And they're linear. One possible solution, one and only one, infinite number of solutions, or no solution. One of those three. And the amazing part is when you go out into space or something like that, and you have not equations of lines, but equations of planes, one thing is one and only one solution, one is an infinite number of solutions, and one is no solution.
Inclined only have 2 points of interception at max if they were on the same orbit.
Like this?
Yeah, if they're inclined differently, they have 2 points of contact.
Oh, but they'd have a line of
Well,
contact.
yeah, one line of contact.
Yeah, which is an infinite number of solutions. Yeah. So even though you have more positions in it, yeah.
Yes.
Okay, Justin decided he'd come back today too. Good. All right. Hopefully some more will be coming in. All right. So that's what we have with possibilities of that. Now, there's also periodically in this text, just about every section will have a linear algebra applied. And this one happens to be talking about chemical reactions and how you can set this up and solve some fairly complicated reactions using linear algebra. I'm going to take that a step further. Drug manufacturing. You can combine some of these hydrocarbons and all these things in a variety of ways, and just changing a little bit, say, of, well, let's just take this as fairly common. You know what sugar is, right? If I'm not mistaken, Splenda maybe is just one little change to the molecular structure of sugar, which keeps the sweet taste, but doesn't damage pancreas or things like that. So it wouldn't lead to diabetes. So I believe that's Splenda. One of them is supposed to be just a very chemically almost identical, just a little bit of difference, so you keep the taste but lose the calories, basically, because your body can't metabolize it if it's different. So when you're doing drugs, you might try, well, this seems to work, but this has this negative side effect. Well, let's try little deviations here and there, see if we can get something that does the same thing without the side effects. And basically, they don't do this. They don't try these drugs on mice anymore. They first do it linear algebra, come up with the possibilities, and then pick out the best, what they think are the best candidates, and then just try those. Saves a lot of time and money and effort. Same thing really with second?
You have this like computer protein simulation.
Exactly.
Well, you can simulate drugs and
Right.
proteins in the body as well.
And they do things like aerodynamic car design or plane design or other things, and they do a lot of stuff using linear algebra with the computer simulations before they ever build the first prototype. Because prototypes are pretty expensive to build. They make sure it works on paper, in Netherland out there, first, and then try it, and saves a lot of time and effort. So let's move on, now that we've got that done, with example 4. Okay? Top of page 5. We're going to give some new words to what we were just saying. Here's an equation, x plus y equal 3, with another in its system, x minus y equal negative 1. Now I'm not going to go back and do it the other way. I'm going to do this the easy way. This is so easy to solve. Just add those two equations together. That eliminates the y, right? So what do you get? 2x is equal to 2. X equal 1. Then plug that back into either one of them. You want to use top or bottom, I don't care. top one. That'd be 1 plus y equal 3. So y is equal to 2. There's your solution. 1, 2. Ordered pair, 1, 2. And you can plug it into the second one, make sure that still works. 1 minus 2, minus 2 would be minus 1. Yeah, that works too. Okay? There's a solution. Okay. Now, if a system of equations, like this one, and like the first one we did at the end of the class last time, has a solution, we call it a consistent system. Okay? And this and the other was a consistent system. If it has a solution, it's a consistent system. These two, the one before and this one, happen to have one and only one solution, still a consistent system. Okay, let's do another one. X plus y is equal to 3, and 2x plus 2y is equal to 6. What can you tell me about those two?
They're going to be all solution because you divide the bottom one by 2.
You get the top one. So those are exactly the same line. So guess what? They have a solution. In fact, they have an infinite number of solutions. Still a consistent system, though. However, this one is a dependent system, and you actually gave the reason, because the second equation is a multiple of the first. That makes it a dependent. One equation depends on the other, so they're not independent, they're dependent on each other. The first two, they're independent of each other.
So I guess any system that has all solutions where the lines are identical.
Okay, now, okay, it's not all solutions, infinite number of
Sorry,
solutions.
infinite solutions, then they would be dependent. Because
Yeah, that's dependent. The two equations are dependent on each other, but they're still a consistent system because they do have a solution. In fact, they have an infinite number of solutions. So they're consistent, but those are dependent, these are independent. They're both consistent. That one's dependent, this is independent, because those are independent equations of each other. So let's do the third one. This is x plus y is equal to 3. Notice I use that in all three of these. And the second one is x plus y is equal to 1. What about those?
that one won't have any solution.
No solutions, because x plus y can't be 3 and 1 at the same time. It's one or the other, but not both. So those are parallel lines, if you think of them in graphs. No common points, no solution. We call that an inconsistent system, because it can't happen, okay? And you don't even bother about saying independent or dependent because it's inconsistent. We don't even mess with that. So that's an inconsistent system, okay? Now, the graph of these two, they actually graph it. The first set is something like that, one and only one solution. The graph of this next one, there's one graph, there's the other graph, right on top of each other. Infinite number of solutions. Anything's a solution to one, it's a solution to the other, okay? And the third one, since the first is like that, the second is like this, okay? Narrow the twain to be, they're parallel lines, no solution, inconsistent system, okay? So, when you have a system of linear equations, not just 2 by 2s, you know, 2 equations, 2 unknowns, for any system of linear equations, precisely one of the following is true. The system has exactly one solution. Consistent, independent. Okay? Number 2, infinite number of solutions, consistent but dependent. Number 3, inconsistent. No solutions whatsoever. Okay? Inconsistent system. All right. Now, 2 by 2s are pretty easy. Wish we only had to do those. In fact, most of your time in math, probably up till now, you've been stuck on 2 by 2s. Okay? You didn't really like them much then. Wait till you get to the 3 by 3s. Okay? They get even worse. So here's a question. Y'all don't have books yet, so I'll write it out in gory detail. X minus 2y plus 3z is equal to 9. That's a z there. Okay. Minus x plus 3y is equal to minus 4. 2x minus 5y plus 5z is equal to 17. There's one system of equations. Here's another system of equation. X minus 2y plus 3z is equal to, I think that's a 9. Yeah, 9. Exactly the same first equation as the other. But the second equation is a little bit different. And that means Muhammad's here. The second equation in this system is x plus 3z is equal to 5. No, I'm sorry, y plus 3z is equal to 5. And the third equation is really simple. C is equal to 2. Okay? Now, which of these two systems of three equations and potentially three unknowns, this one, two of the equations have three unknowns, one only has two. That one, only one has three unknowns, but the second one has two, third one only has one. Which of those three systems would be easiest to solve?
So the second one, like,
Yeah, the second one, because guess what? You already got one of the variables right now, 2. And then all you have to do is plug a 2 into the second equation, and you can get the y. And then plug those two in, and you get the x. Ah, piece of cake. Or maybe marble cake. It's a little hard, but not bad. Okay. But anyway, you got it. This one,
you can start with the second one, I think.
What's that?
The second one, because it's the less variables to solve.
Okay, you can't solve it, but you can come up with a relationship
Yes.
that, say, x is equal to 3y plus 4. Then you can put that in there, and then, yeah, you got everything in y and z, and then you can do those two, but that's still
Long distance.
along. Okay. Now, what if I were to tell you that these two are equivalent systems? That would be nice, wouldn't it? Then you know if you got that solution, that's also going to be the solution as well.
That last one on the right, z equals 2, that's the equation of a plane, isn't it?
Well, anything with three variables in it, in linear, is a plane, yeah.
Right.
Yeah.
Just
So, yeah, all three of those are planes, and they intersect at one point, okay? One goes this way, one goes this way, one goes that way, or something, and they have a single point intersection, okay? Now, what we did, and what y'all were describing to me, is what we call back substitution. If you can figure out what this is, which is pretty obvious, then substitute this in here, you can figure out what y is. Then plug both of those in here, you can figure out what x is. That's called back substitution. And you get all three variables at the one and only solution that you have for it. Okay? Now, they're going to have us doing this one's really hard, so put on your hard math belt, okay? It's x minus 2y is equal to 5. And y is equal to minus 2. Can you solve that for me? Please say yes. Huh? Okay, I thought not. Okay, never mind. Okay. What would it be? X? X equal or x?
Yeah, X equal.
X equal what? Okay, 5. Second?
X should be equal to 1.
It's going to be 5
Minus. It's 5 plus 2 times minus 2, right? That would be 5 minus 4 equal 1. Right? Okay. Now, let's see, make sure that is right. If you put a 1 in here, minus and minus 2 is minus 2 times minus 2 is plus 4. that was hard, wasn't it? Well, all your test questions were that hard, right? Okay. Now, so it has one and only one solution. That solution is, and here's how we write our answer: x, 1, y, -2. Always ordered pair. Okay. Now let's do the one. I think that's at the top of the page, so I didn't have to write it again. Okay, let's do that. We already said we know z is equal to 2. What's y equal to? Got it? And then let's do x.
X plus 2.
Yeah, but, okay.
9 minus 2.
2.
Plus 6.
Only minus 6, yeah. Okay. So your solution there would be 1, -1, 2. After a while, it's going to show up. Okay. Now, let's just check and see if that works. 1 plus 2 is 3, plus 6 is 9. Yes? And -1 plus 6 is 5. And 2 is equal to 2. Yeah. Works nicely. Okay. Back substitution. Okay. Okay. Now what we say, I've already used the term without definition. Two systems of linear equations are equivalent when they both have the same solution set. That's what I said before. That system there, this system here, I'm just telling you ahead of time, they're equivalent. Because, let's see, it's not that hard to check. We know already this is the solution for this set, right? Let's see about this one. 1 plus 2, well, that's the same thing we just did. Plus 6 is equal to 9. Yeah. Let's do this one. -1 minus 3 is equal to -4. Yes, that one worked. Let's do this one. 2 plus 5 is 7. Plus 10 is 17. Yes. So guess what? Since that solution set works for this one as well as this one, we say these two are equivalent systems. Now we didn't know it until we put them in, and then we knew they were. Okay? Now, there's got to be a way to get from this to that, knowing that we're going to have an equivalent system. There are 3 rules we have to follow. Okay? And the first one makes perfect sense. Okay? Each of the following operations on a system of linear equations produces an equivalent system. The first one, if you exchange any 2 rows. Of course, it's the same system. You just change the order. Whatever solution to one is going to be solution to the other. That's pretty easy. Interchange any 2 equations. Okay? Number 2, multiply an equation by a non-zero constant. Well, we were doing that kind of before, weren't we? What if we multiplied the second equation by 2? Then that would be minus 2x plus 3y is equal to -8. Yeah, that's going to have the same solution. So multiplying any single equation by a non-zero, don't ever multiply an equation by 0, okay? Just don't do it. You lose all meaning of the equation. Everything goes to 0, you say, whoopie-doo. So, don't do that. But any non-zero number, you can do. Fraction, decimal, rational, irrational, doesn't matter. You'll get an equivalent system. So, exchanging 2 rows and multiplying by a constant. Now, here's, yeah.
If I can solve the problem and I want to get an answer, can I just multiply by 0 and get rid of it?
Yeah, exactly. And then you have solved your problem, haven't you? You have no solution, whereas there could have been one, huh?
I got rid of the problem.
You got rid of the problem, but guess what? If the boss wants an answer to it, you haven't gotten rid of your problem. You got a bigger problem, okay? Never mind, okay. Never mind, okay. Now, this third one isn't as immediately obvious, but here's what you can do. So exchanging two equations, multiplying any one equation by a non-zero constant, that will keep it equivalent. But here's the next one. This involves 2, okay? Add a multiple of one equation to another equation. That's also an allowed operation, okay? But guess what? We have done that before. Remember the one that went something like, let's see if I can find it again. Doesn't this work? Oh yeah, there it was. X plus y equal 1. Come on, okay. And x minus y, no, x plus y is equal to 3, and x minus y is equal to minus 1. Okay? Remember what I said was a real easy thing to do here? Add the two equations together. Well, just like you can add two equations together, you can add a multiple of one of these to the other one, and that will still work. That certainly is an equivalent operation. Okay? An operation that will produce an equivalent result. Add these two together, and you get 2x equal to 2, x equal 1. Those are all equivalent systems. Okay. So, I turned back a page. Forgot to turn it back again. On page 7, left-hand column, in the sort of the margin column there, you see a picture of Carl Friedrich Gauss, German mathematician, also scientist, engineer. I mean, yes, the original units for the magnetic field is Gauss, okay, named after him. There's something, an equation you use called the Gaussian, okay, well, and we're going to use some things in here. The Gauss-Jordan elimination method. Gauss shows up all over the place, okay? He, and they say here, is recognized with Newton and Archimedes as one of the 3 greatest mathematicians in history. I'm sure you could get other people that might have other top 3s, but he's usually real close to that. And even though this method that we're going to be talking about is called the Gaussian method of solving systems of equations by back substitution, the Chinese came up with it about 1,000 years before he did. So he wasn't the first, but he was the first Western mathematician to discover it. So he didn't know the Chinese had already done it. Okay, did a lot of stuff, incredible stuff. Okay, let's go to example 7 and see if we can get it done. By the way, that could be a potential paper topic. Or, how did he develop the Gaussian method? Or, how did he come up with, what did he do to get the Gauss named after him? There's lots of potential paper topics just with that one individual. Okay, so here we have a system of equations. X minus 2y plus 3z equal 9. Hey, we've seen that before. Minus x plus 3y is equal to negative 4. We've seen that before, okay? And 2x minus 5y minus plus 5z is equal to 17. Yes, we've seen this exact system before, okay? And then out of the thin air, they came up with an equivalent system that was real easy to solve. Well, guess what? We're going to become the thin air. We're going to show you how that came about, okay? Now, here's the technique, okay? ideally, you want the first coefficient of your first equation in the system to be a 1. Guess what? We got it. Toyota. It's there. Okay? So, we already got the first thing done that we wanted. We want that to be a 1. Now, the second thing we're going to do is figure out a number to multiply this first equation by. When we add it to the second equation, we eliminate the x. We don't have to think very far. Multiply it by 1, or just add them, and sure enough, you're going to eliminate the x. So you see what we're doing there? Add equation 1 to equation, I can't write, 2. Okay? So what I'm going to do, I'm going to leave that first equation alone. X minus 2y plus 3z is equal to 9. See it? Now, I'm going to add the first two equations together. And what do you get? Add the first two, and what do you get? Yeah, x minus x is 0. Okay? Add the next two terms. That would be y. Okay? Add the next two terms. Plus 3z is equal to, add the constant terms, 5. Equal 5. We've done it. Okay? Now, the next step is just a tad harder. Now, I'm going to abbreviate a lot more than I did here. What I want to do is take that first equation, same first equation, and find the number I can multiply it by, that when I add it to the third equation, I'll eliminate the x. And that's pretty obvious too. What would that be? A number I can multiply the first by, add it to this one, and eliminate the x. Negative 2. So that's exactly what I'm going to do. Now I'm going to abbreviate even more so. Minus 2 E1, that's equation 1, plus E3. That's equation 3. So let's do that over here. Minus 2 times x plus 2x is 0. Minus 2 times minus 2y would be 4y. Okay, minus 4y minus 5y would be minus 9y. Okay? No. Minus 2 times minus 2 is plus 4y. So that's, you're multiplying. Multiply minus 2 times equation 1. Ooh, oh, yuck. My eraser's not working. Okay? So minus 2 times minus 2y would be plus 4y plus minus 5y would be minus y, right? Yay? Minus 2 times this would be minus 6z plus 5z would be, second? Minus 6z plus 5z minus z. And minus 2 times 9 would be minus 18 plus 17 is equal to minus 18 plus 17. Minus 1. Okay? All right, here's Vince. Slowly we're getting a class. Okay, we're still missing Daniel and Jordan. And again, all Y chromosomes. Okay. Where's the beauty? Never mind. Okay. Now, okay. First thing we wanted was 1 as a coefficient for your first variable. We got it. It was there already. Next thing we wanted was zeros below that. So you're going to multiply the the first equation by something, when you add it to the second to give you a 0 there, you didn't have to multiply anything, just add it. And that gave us our second equation. We did the same thing here. This time it took multiplied by -2 and adding to this to eliminate the x there. And then we got what we had left over. Okay. Now the next thing we want to happen, lucky us, we want the coefficient here to be a 1. Go to the next equation. First non-zero coefficient we want to be a 1. It is. Oh, how fortunate we are. Okay? Now what we want is the thing below that to also be a 0. How do we get this to make that a 0? Add them together. Okay? So let's do that. This will be equation 2 plus equation 3. That's going to be what we're going to do next. So this becomes, first equation stays the same, x minus 2y plus 3z is equal to 9. Second equation stays the same, y plus 3z is equal to 5. Third equation, when you add those two together, what do you get? Second? Well, there aren't any x's. Add equation 2 to equation 3. Okay, 2z is equal to 4. Okay? Now guess what we want the next step to be? You want the coefficient of the first non-zero coefficient in the third equation to be a 1. How can we make that a 1? The first non-zero coefficient in the third equation would be a 1. Right now it's a 2. How do we make that become a 1? Divide by 2. Or multiply by 1/2. However you want to say it, you're multiplying by a non-zero number. Multiplying by 1/2. So what does that become? Z equal 2. And look at that, and you go right back. That's what we had at the top of the previous page. X minus 2y plus 3z equal 9. Y plus 3z is equal to 5. Z is equal to 2. Those are equivalent equations. The two systems are equivalent because we use only those three operations. We didn't even use one of them. We didn't exchange any two rows. We could have. That would still been equivalent. We didn't even need to. Number two, and we did this a lot, we added a multiple of one row to another row, or one equation to another equation. We did it there, we did it there, and we did it there, okay? And third, we multiplied an equation by a non-zero number, and we multiplied that by 1/2. Or divided by 2, that's the same thing. Okay, just like you never multiply an equation by a 0, you also never divide an equation by 0, because that's completely undefined. So as long as it's a non-zero number you're multiplying or dividing by, perfectly okay. All right. So, and then we've already solved that system. Remember, we did that at the top of the previous page. We got that the solution set was 1 minus 1, 2. You know the 2's right because z is equal to 2. And you can plug in the others and you see you get minus 1 for y and plus 1 for x. Okay. Now, if you were to, and I'm not about to, try to graph those three equations. The first equation's a plane, the second equation's a plane, and the third equation's a plane. And those three planes are going to intersect at one and only one point, and there's the point. 1, negative 1, 2. Any two of those planes intersect at a straight line. But then the third plane intersects both of those at a point. Okay. And here's Daniel. Now we're down just to Jordan. All right. All right, we just finished example 7 on page 7. And now we're going to move to, And then they go back and plug in to make sure they work. We had already done that, so we're not going to do that. So let's see what it looks like. We know in a 2x2 what an inconsistent system looks like. They're almost obvious, okay? A 3x3 can really be disguised, okay? You don't know what's going on there, okay? So I think I'm going to erase this and go to a clean sheet. Is that okay? Okay. I didn't get to grab a snack between my last two classes. I'm so rapidly running out of energy, it's amazing. As if I didn't have a lot of storage here, but it's slow release. Okay. So here's example 8. Here's a system. X sub 1, this time I'm not using X, Y, and Z, but X sub 1 minus 3X sub 2 plus X sub 3 is equal to 1. 2X sub 1 minus X sub 2 minus 2 X sub 3, is equal to 2. And X sub 1 plus X sub 2, plus 2X sub 2 minus 3X sub 3 is equal to minus 1. Okay? 3 equations, 3 unknowns. Okay, now your unknowns are x1, x2, x3, not x, y, and z. Doesn't matter what you name them. Okay? Okay. We're going to start the same process we just did. What was the first thing you remember that we wanted to happen here? The leading coefficient, we want to be a 1. Guess what? It already is. We don't have to do a thing with it. It's already there. Okay? What's the next thing we want to happen? We want this to become a 0. So that means we're going to have to multiply something by the first equation and add to this to make this term go away. What would that be? Negative 2 times equation 1 added to the equation 2. So negative 2 E1 plus E2. That's what we're going to do. All right. Now, keep the first equation as it is. E1 minus 3x2. I said E1. X1 minus 3x2 plus x3 is equal to 1. Okay. Now we're going to do what it told us to do. Minus 2 times equation 1 added to equation 2. So minus 2 times x1 is minus 2x1 plus 2x2 plus 2x1 will be 0. That's what we wanted. Okay? Minus 2 times minus 3x2, that would be 6x2 minus x2 would be 5x2. Sorry about this. Goodness gracious. Can I just go to sleep? Okay. All right. What's that? Oh, yeah, something. Okay. So minus 2 times x3 would be minus 2x3. Minus 2x3 would be minus 4x3. And minus 2 times 1 would be minus 2. Plus 2 would be 0. Right? Are y'all doing this with me? Okay, I don't want to be the only one doing the work here. I already know how to do this. Okay? So y'all need to be doing the work. Okay? What's the next thing we want to happen? We want this one to become a 0. How do we make that happen? Say again. Using the first equation. Yes, multiply the first equation by negative 1 and add it to the third. So minus equation 1 plus equation 3 is going to be the new equation 3. So do that. minus x1 plus x1 is 0. Minus 1 times minus 3 would be 3x2 plus 2x2 would be 5x2 minus x3 minus 3x3 would be minus 4x3, right? And minus 1 would be again, minus 1, that's minus times equation 1, and my writing stinks. Let me make that a little cleaner. I can hardly read it. Okay, so it's equation 1 minus equation 1 plus equation 3. Do it with the constant term. Minus 1 plus a minus 1 is a minus 2. Right? All right. Now, if you don't get so focused on a single tree that you miss seeing the forest, okay, let's take a look here. This looks like something sort of like something we did before. On the left-hand side of these two equations, you have 5x2 minus 4x3. They're the same things here, equal to different things over there. Can that ever happen? Say again?
Yes.
How? No. If this is identically the same on this side, it's going to be identically the same on that side. Can't have it otherwise. Okay? So guess what? This is an inconsistent system. There's no number you can put in here. No number you can put in here and here. Two set of numbers here and here. But the same two numbers here and here and get different results. You can't do it. Not in our number system. Okay? It cannot happen. So this is an inconsistent system. Okay? There is no one single number that will satisfy all three of those, because there's no one single ordered pair of these two that will satisfy that equation. So it can't happen. Okay? Now you could take it one more step, okay, if you wanted to, or you convince yourself. What could you add or multiply by that one to add to this one to give that a 0? Negative 1. So negative 1 times that would be negative 5 plus 5 is 0. But when you do that, that would be a plus 4 minus 4 would be 0. And then that would be a 0 plus a negative 2 would be negative 2. You get 0 equal negative 2. How often does that happen? Never. You can't have it. Inconsistent system. So anytime that you're going through one of these series of operations, doing all legal steps, every step you took was legal, and yet you get something that can't possibly be inconsistent system. Okay? Now, inconsistent system when you had lines were two parallel lines. Inconsistent system when you have planes can be a whole variety of things. Okay? It could be one plane's up here, the other plane's over here, and the third plane's down here. Well, these two intersect here, these two intersect there, these two intersect there, but not all three ever intersect. That would be an inconsistent system. A plane here, a plane here, and a plane here. They're all parallel to each other. That would be an inconsistent system. Or like this one, if I'm not mistaken, they draw the picture here, and it's really hard to follow their picture. They have a sort of a purple plane, a pink plane, and a green plane. Okay, let me pick two that are easy. The pink plane and the green plane intersect in a line that goes like that, but the purple plane and the pink plane intersect at the dotted line that's behind that. They intersect in a variety of ways, but there's no single point where they all intersect. All those three lines never intersect. Okay? So, not going to happen. All right, inconsistent system. Okay? Let's do example 9. Now, don't make any false assumptions here. When you look at example 9, it looks like it's missing a lot of terms. It has nothing to do with how many solutions it has. Just happens to be that x2 minus x3 is equal to 0. x1 minus 3x3 is equal to negative 1. And minus x1 plus 3x2 is equal to 1. Okay, that's missing a lot of terms there. Has nothing to do with what your answer is going to be. What's that?
First you got to multiply, you got to get rid of x1 on solution 2 and 3.
Okay. I'm almost certain I followed what you said, but say it one more time.
Substitute like 2 and 3 together. Put solution problem 2 and problem 3 together.
These two?
Yes.
Add them together?
Yes.
Okay, that certainly will work. Okay? That's a legal move. And what do you get then?
You got 3x.
0 here.
Yeah. Got 3x2.
Yeah.
Minus 3x3.
Okay.
Equal to 0.
Equal to 0. And then you compare that with that, and this one would be just 3 times what that is, right? That is a dependent system. It's got an infinite number of solutions, but you don't really see what the solutions are. You just see they're the same equations. But you don't get a feel for what the solutions are. So, yeah, you can see that it's a consistent system and that there's infinite number of solutions, but you don't see what they are. So I'm going to show you a method that actually tells you what they are. Okay? Now, what was the first thing we like to have in the others when I was doing them? The other two we did before. Maybe 3 we did before, whatever. What the first thing you wanted was the first you wanted the first coefficient to be a 1. This one's a 0. Okay? We don't like that. We don't really want that to happen. However, this one's a 1. And what was one of the allowed operations? Exchange 2 rows. So that's what we're going to do here. Exchange these 2 rows. I'm calling them rows. Equations. Okay? We're going to do equation 1 and equation 2 are going to swap places. Okay. I know this is a little more involved than what you did. That just showed that it was a infinite number of solutions, but it didn't tell you what those solutions were. So this becomes x sub 1 minus 3x3 is equal to minus 1. X sub 2 minus x sub 3 is equal to 0, and we leave the third one alone, minus x sub 1 plus 3x2 is equal to 1. Okay. Oh, my eyes are so dry. All right. So, that's what we wanted first. We wanted 1 to be the first coefficient, and we got it, just by exchanging 2 rows. What did we want next? This to be a 0. We got it! Done! Okay. What did we want next? That one to be a 0. How do we get it? Add those 2 together. All right. So let's do that. We'll add row 1 to row 3, or equation 1 to equation 3. Okay? So that would become, we keep equation 1 the same, which is x sub 1 minus 3x3 is equal to minus 1. We'll keep equation 2 the same. X sub 2 minus x sub 3 is equal to 0. Okay? And we will add those two together to give us our new equation 3. So what does that give us? Okay? X of 1 minus x of 1 is 0. Good. Add these two together. 0 plus 3x2 is 3x of 2. Add those two together. That's pretty easy. Minus 3x of 3. Okay? And then you add those two together and you get 0. So you wind up almost with the same thing you got. Okay? Huh? Yeah, it's the same thing. Okay? Now, what we're going to do is eliminate that third one. And how are we going to do that? Okay, let's go over what we want. Okay, yeah, this second. We wanted a 1 here, 0 is what? Got it. Next thing we wanted a 1 here, 0, but it doesn't matter about both. We want this to be a 0 here. So multiply this one by -3, add it to that. Okay? -3 row 2 plus row 3. Equation 2 plus equation 3. Okay? Now we're going to leave 1 alone, so that's x sub 1, if I could read it, minus 3x3 is equal to minus 1. We'll leave 2 alone, that's x sub 2 minus x sub 3 is equal to 0. And now the third one, when we multiply minus 3 times the second, add it to the third, what does that give us? 0. Next one would be 0. And the next one would be 0. So you get 0 equal 0. Okay, folks. When is that true? Always. Okay, now before we would come up with stuff like 0 equals -1 or -2 or something. That's never true. No solution. Inconsistent. This one, when you get one line that they're all zeros down here, so anything would make that work, then that's infinite number of solutions. Now, you might say, but we still haven't figured out what those solutions are. Well, actually, we kind of do. These that have ones as a coefficient, we call them leading ones. Those are variables. This one we don't have a leading one. So we basically let that become a parameter. Okay, now what are the favorite names for parameters? Does anyone know? A lot of times they love T. S's are good, but T's usually everybody's favorite. So what we're going to do is say let x sub 3 equal T. Now, plug that in here. Well, this says x sub 2 minus T equals 0. So what can we do there? X sub 2 is also equal to T. Okay? And then plug that in, also plug it in up here, and you have x sub 1 minus x sub 3 is T minus 3t is equal to minus 1. Well, let's solve that for x of 1, and that would be 3t minus 1, right? So here's your ordered triplet in this case. Your x of 1 is 3t minus 1, your x of 2 is t, and your x of 3 is t. Give me a t! 10. So this would be 29, 10, 10. There's the solution. Give me another t. Any t. Second? 8. Okay? This would be 23, 8, 8. There's a solution. Give me another t. 5. Is that what you said? Huh? 5. This would be 14 by 5. There's a solution. Y'all like hard things, don't you? How about t equals 0? What would that be? -1, 0, 0. There's the solution. Let's see if that works. 0 minus 0 is 0. Yeah, that works. -1 plus minus 0, negative 1. That works. And 1 plus 0 is 1. Yeah, that works. Okay. And you could have tested all those others too, but it would take me a lot longer. But yeah, every one of those solutions will work. 3t minus 1, comma t, comma t. Got to work. That first equation tells you that x2 equals x3. So whatever they are, that's the same thing. T and t. Okay. All right, good deal. Now there's a little discovery at the bottom of the page. Do we have time for it? Well, we may have time for the first line of it, so let's give it a shot. It says graph the two equations. Can we get by without graphing? Please say yes. Let's see. Okay. I'm not going to graph them, but we're going to solve them an easy way. X minus 2y is equal to 1, and minus 2x plus 3y is equal to negative 3. Now, the easy way to solve that is multiply the top equation by 2 and add to the bottom, right? So let's do that. 2 times the top and add it to the bottom. So that would be 2x minus 4y is equal to 2, and minus 2x plus 3y is equal to minus 3. Add the two together, and you get negative y is equal to negative 1. And what will y be then? It's pretty easy. Say again? 1. Y is equal to 1. Okay? Let's plug that back in either one of those. So I like the first equation. So x minus 2 times 1 is 2 equal 1. So x is equal to, add 2 to both sides, 3. Okay? So we're claiming that 3, 1 is a solution. Okay? Well, let's see if it is. 3 minus 2 is 1, and minus 6 plus 3 is minus 3. Yeah, that is a solution. All right, let's go back and do Gaussian elimination. That's what we were doing before. I don't know if you caught that. That's why we called it that, Gaussian elimination. We're going to start with this. You remember that 3, 1 is your solution? Y'all remember that, won't you? Okay. I'm going to erase this. Well, actually, I shouldn't have. Let's do that. X minus 2y is equal to 1, and minus 2x plus 3y is equal to minus 3. Okay? Doing Gaussian elimination, remember what do we want the first thing to be? Leading coefficient 1. We got it. We don't have to do a thing to it. What do we want to happen next? Second? We want the leading coefficient of the next one to be 0. How do we make that happen? Yeah, we multiply 2 times the first one, so 2 times equation 1 plus equation 2. I shouldn't have done the other. That's exactly what, whoops! It's exactly what we did before, and I don't, not wanting to give it away, okay? All right, so that would produce, keep the first one alone, x minus 2y is equal to 1, and then do that. 2 times x is 2x minus 2x is 0, and 2 times minus 2y would be minus 4y plus 3y would be minus y, and 2 times 1 is 2 minus 3 would be 2, yeah, negative 1. Okay, 2 minus 3 would be negative 1. So there we have y is equal to 1. Then back substitute, and you have x is equal to 1 plus 2 equals 3. We got our same answer. In fact, almost the same way. Okay? So yes, Gaussian elimination will produce the same result as elimination by addition. That's what we call that first technique. So we have finished section 1.1. Homework exercise? Yeah, pretty exciting, huh? Any of the odds 1 through 5. Number 2, the second group, any of the odds either 7 or 9. In the third group, any of the odds 11 through 23. There's a whole bunch there. Next, any of the odds between 25 and 29. Next, any of the odds 31 to 35. Next, any odds between 37 and 55. Next, any of the odds either 57 or 59. Either 61 or 63. Try to do 65. 67 is a true false. And then try to do 69. Then do either 71 or 73. Do 75. Do any of the odds 77 to 81. Do 83. And then if you want to write about 85, you can. Or 67 is to show that. And 89, I said 67, 87. 89 yeah, try 89 and try 91. Now, why did I give you odd numbers? 2 reasons. And in the back of the book, the answers for odd numbers are there. So if you do the problem, get the answer in the back, move on. But if you do not get the answer in the back, can't figure out how they got it, then you can go to, this shouldn't be anything new to you, calcchat.com or worked out solutions to the odd number exercises. So if you go to that website, absolutely free website, you don't need a code, anything else, anyone can go to that website. You don't actually have to have the book, except to know what the website name is. Go to calcchat.com. You'll have to navigate around to find it, but you can find all the odd number exercises worked out for you. So if you can't get the answer in the back of the book and can't figure out how to get it, go to the website, and it should show you. If you still can't understand how they did it or why they did that step or whatever, bring it to class and we'll work it out. Okay? So any questions? We'll begin with 1.2 next time. Now, I swear I thought I started the page with a marker in my book and now I can't find it. I'll put it there. All right, any questions? I think we're out of time, aren't we? Okay. So, yes?
Have you got the code for this book yet?
No, I haven't, but I'll try to get it. I'll work on that tomorrow. I don't have any time today because I may have a little time at the end of the class, but tomorrow will be the better chance for me to get that. I won't get the code, but I'll get it started to get it. Do you need that in order to access it? You do, okay. Some students have told me they're able to access it without a code. I don't know how they're doing it, but they told me that. Not this book, but other Cengage books. So I'll try to get those codes. Get started on getting the codes tomorrow. If I can get enough done, hopefully I'll have the codes by Monday. No, Tuesday. Because you do know the good news, bad news situation, don't you?
We have no class.
The bad news is school is closed Monday. There are no classes. But the good news is it doesn't affect us any. We meet on Tuesday and Thursday. So we will have a full week next week in this class. Not in the other class, but in this class. Isn't that a joy?